In this lesson, we're going to look at state changes and the energy required to change phases. What we're looking at here is what's called a heating curve. There are a few things to notice about this. The first of which are the x and y axes. On the x-axis, we see we have heat added, so as we go from left to right, we're increasing the amount of heat or the amount of energy added to the system. On the y-axis, we see the temperature, so we start at something where below zero, and we increase as we go up to some temperature above 100 degrees. The reason we have 0 degrees and 100 degrees on this particular heating curve is because we're looking at water. Similar heating curves for different substances would have different temperature cutoffs. So what we're looking at in the curve is as we add heat, or as we add energy, what we see is that the temperature of the solid form, which in this case is ice, increases until it gets to the point where we have solid and liquid both present. At that point, the temperature increase stops and we're only changing phase. So here we have liquid going to the solid phase. Once all of the solid is converted to a liquid, then additional energy that's added can then heat that liquid until we get to the boiling point. So we heat it up, then we change phase, then we heat it up again. Notice that we can either be changing the phase or changing the temperature. We cannot do both at the same time. Once we get up to the boiling point, or the point of vaporization, we can go from the liquid into the gas. So along this line, we are changing from liquid to gas. We're still putting energy in to make that change happen, but there's no temperature change happening. We're just adding heat to have the phase change. Once all of the liquid is converted to gas, additional heat or energy that's added will result in the gas increasing in temperature. Here we're looking at the enthalpy, and so what we're looking at is the energy required for a phase change to occur. Typically, this is given in units of kilojoules per mole, but it may also be seen in joules per mole or calories per mole, and sometimes we'll see it in kilojoules per gram or calories per gram. And what we'll see is that this depends on the amount of substance present. So the bigger the mass, or the bigger the moles of sample we have, the more energy it's going to take to go from the liquid phase to the gas or from the solid to the liquid. But we can calculate that value using these enthalpy values. These enthalpy values are reference values that are given to you to solve the problem. So you don't have to memorize them. You just need to make sure you're looking at the right phase change and that you're looking at the right substance. So let's look at an example of how we would use this. The enthalpy of vaporization of methane is 8.18 kilojoules per mole. How much energy is required to vaporize 2.5 moles of methane? So this is going to be set up much like our dimensional analysis problems that we've already done. We're going to look for the simplest unit to start with, and then we're going to look for the conversion factor, or the relationship that's going to help us get from what we start with to what we want for our answer. So let's look at this. We're going to start with our 2.5 moles because that's the simplest unit, and then we have to look at the relationship that's given in the problem, and we see that we have 8.18 kilojoules per mole. Now notice the moles goes on the bottom because we have moles on top in our first step, and we want to cancel those out. So just like we solved when we were looking for meters to centimeters or miles to feet, any of those we were worried about the units. So we see that moles is going to cancel out, and what we're left with is units of kilojoules. So we can then do the math and get 20.45 kilojoules. Remember, the moles canceled. We do have to go back and look at significant figures, and we see that we have 2 significant figures in 2.5, we have 3 in 8.18, and so as a result we need to round our answer to 2 significant figures.